Welcome. My name is Ben Houston, and we are here today to talk about peak flow estimation tools for culvert and catch basin assessments. First, a little background on me. I'm a licensed environmental engineer, and I've been doing topo mapping my entire career, starting back as a second lieutenant in the Army Corps of Engineers almost 30 years ago. I started working with LiDAR data around 2003, which was the time when the FEMA Appendix A incorporated LiDAR and became the sort of gold standard for using LiDAR in topo mapping. Back then, I managed a portion of the New York State floodplain mapping program when we first pioneered the use of LiDAR data for floodplain mapping. And the story now, 15 years later, of drainage and peak flow estimation is really a story about LiDAR. But before I get too far along, this is what I'm going to walk you through in the next half hour or so. We're going to talk about the Water Resources Institute and what they're up to, talk about some standards for data, and then how to integrate LiDAR with both of those to generate runoff characteristics and peak flows. And then we'll apply that to some case studies so you can see how it all works. So the focus back in those Appendix A days of LiDAR was really on the floodplain itself, both in cross-section and in profile, and establishing whether LiDAR data could really adequately characterize the physical world. The gold standard was FEMA 2-foot contours, right? LiDAR data typically had a post spacing of about 1 meter and a vertical accuracy of about 6 inches. So fast forward to now, and the data is getting better. We have drones now that give us ridiculous detail. LiDAR data is ubiquitous. Local LiDAR updates have higher resolution, more points, and more detail. So now we want to be able to use that data to start looking outside the floodplain at the landscape that's actually contributing runoff. In my neck of the woods, when local municipalities are dealing with wet weather events, the big story is not so much about large-scale inundation, but about streams and roads. Washouts, maintenance, culverts overtopping, it seems to be an ongoing problem. Of course, there's always the big kahuna that buries a subdivision in 3 feet of water or wipes out a trailer park in the floodplain. But in Ulster County, where I live, they wanted to do a better job of predicting which culverts and road crossings were more likely to get washed out and be able to look at where to upgrade or modify before, not after. So they linked up with the New York State Water Resources Institute, which has been working on developing some GIS-based predictive tools for culverts using public domain national data sets. So the Water Resources Institute is actually housed in the Department of Bio and Environmental Engineering at Cornell, and they've been developing an extensive GIS-based model. So this is the construct of what Cornell's working on. I don't want you to worry so much about the details. The intention here is to just give you an overall picture of the framework. This is all Python scripts, some of which rely on ArcGIS and some of which are just there to manipulate data in tables and do calculations. So it starts up here in the upper left with culvert data. And if you have good location, you can go down this red path to the right and arrive at this point at the bottom. If you have good culvert characteristics in your inventory, you can go down this other path along the left for culvert inventory and field assessment work, and you can end up calculating the capacity of what's there now. So they both end up here, comparing the two. That makes sense, right? Comparing the capacity of a culvert to the estimated flows that would arrive at that culvert for different storms, so that we can theoretically see which culverts are capable of passing, say, a 5-year storm or a 10-year storm. And then we can prioritize culverts based on which ones perform the poorest or have the smallest differential between what their capacity is and what the anticipated flow is for a given return interval. In that regard, it's not even critical that the flow models are calibrated and exact. It's just that they get applied uniformly for each culvert. What we're after is not so much finding out what the exact peak flow is here, but the ability to rank order culverts and catch basins based on risk. So we're all set to go, right? Well, not so fast. This all works great if you're a grad student and if all your files are in the same projection and coordinate system. And because it's like 8 or 10 different Python scripts that were all developed separately, they only really work perfectly if you keep your right pinky on F8 and wiggle your little toe and scrunch your right eye just right. The point is that while all this works, it's most definitely not ready for prime time, or as we say, written by scientists for scientists. One of the problems with this construct is that it's built on public domain USGS DEMs, which are part of the National Elevation Data Set. And that typically means 30-meter resolution, or if you're lucky, where I live in New York, perhaps you have 10-meter resolution, which is just a resampled version of the 30-meter. It was an academic project, so they wanted it to work. So they started with the 30-meter publicly available DEMs. And they filled sinks to get a depressionless DEM, and we're off to the races. Well, anyone that's ever done a GIS tutorial on how to do runoff modeling in GIS knows that the first thing you do when you download a DEM is you fill in all the sinks to get a depressionless DEM. Because you want all your water to flow downhill, right? Which, if your scale of analysis is 1 to 24,000 and you're in rural Idaho or somewhere, that's fine. But not when you're dealing with local scale catchment delineation, roadside ditches, and culverts, particularly in built environments like a suburban or urban setting. And I'll show you some examples of that in a bit. Now, one of the huge values of this construct that the Water Resources Institute program built is a standard curve number layer that actually extends from Pennsylvania to Maine across the Northeast, and it actually works. But it's 30-meter pixels. So just a brief aside on scale, right? If we're dealing with 30-meter pixels, that means we're using a mapping unit of 900 square meters, which is just under 10,000 square feet, or about a quarter of an acre. So that becomes our minimum mapping unit. But using standard 4-band ortho imagery and LiDAR, we now have the ability to create land cover and hence curve numbers at 1 meter resolution. So we came in saying, hey, I think we can do better. We think we can adapt this Cornell model to the real world and apply it using much higher resolution data. Another huge value to this Water Resources Institute construct is that its reliance on standardized data models, like, for example, Culvert Data. The point here is that Culvert Data model standards do exist. If you use a standard construct, then it's much easier to code against, particularly if you're running, say, capacity calculator scripts. The nice thing about this NAACC, or the North Atlantic Aquatic Connectivity Collaborative data model, is that you can actually download a template, populate it with your own data, and then upload it back to the NAACC for QC and public distribution, so that anyone, like someone with an interest in peak flow calculations, can go and download it. The capacity scripts that Cornell built read in the standardized culvert characteristics that are in the database, like size, material, slope. Obviously, it has to make some assumptions about things like inlet and outlet conditions. But once you have all that, voila, with some 8th grade algebra, you can have a table with the capacity calculated not for just one, but for every single culvert in your inventory. And talking about standards for culverts, we also have a standard for precipitation. Remember, we're not talking about just one storm, but a range of storms, the 1 year, the 2 year, the 5 year, etc. So the Python code is hardwired to read the standard NOAA Atlas 14 precipitation estimates, which you can go and download in a standard format. It'll also read other formats. For example, the Northeast Regional Climate Center publishes similar estimates, which actually include climate change factors, but the tables are transposed. The point is that we want to standardize the precipitation data so that the peak flow calculator can just go and look up a table and know where to find the various values. So now back to our story. But our story isn't really about capacity calculations for each culvert, right? It's about estimating peak flow for specific return intervals and then comparing that to the capacity calculations. Now, we're part of the way there because we just got, the Atlas 14 files from NOAA for precipitation. We have a standard culvert inventory table that we populated from the NAACC template. We have high resolution topo and imagery, and we have a standard curve number data set. But what we really need is what? Drainage area, average slope, average curve number, and time of concentration for any point on the map. And that's where the LiDAR data comes in. And didn't we say at the beginning that this is really a story about LiDAR? So this is what a typical LiDAR data set looks like. And right here, we're just looking at ground returns. This is points off of the sensor with the non-ground removed. So one of the things I want you to note is that the LiDAR data was flown on a different day than the imagery. So as you can see, the cars and the imagery were in different places on the day that the LiDAR was flown. And you can see in front of this darker car, there's some void areas here and here where cars were probably parked when the LiDAR data was collected. One of the things that we get asked a lot about LiDAR data is, can you see the curbs? How exact do the curbs need to be? The surveyor would want to go out there and would want to capture the top of curb along, if you can actually notice where the curb and gutter is in front of the car here, a surveyor would want to capture the top of curb and insert it as a brake line. So, and that's what we would expect. If you see where the curb line is, we would expect most of the flow to actually be in this gutter apron here. So we see this concrete gutter apron. So most of the flow actually is not on the curb, but it's in the gutter. So collecting top of curb brake lines as a surveyor is great if you're just doing 1 acre or maybe even up to 10 acres, but not for 10 square miles or for an entire municipality. It's just not cost effective. So the question is whether the LiDAR data is sufficient on its own without curb brake lines to mark where the gutter and the edge of the road is. So here's an example of that data using a tin. We can actually see in this surface, this triangular integrated network, where the gutter is. And you can actually notice where the void areas are here and here where those cars were. But this is where we might need to put some brake lines in to make sure that the flow actually stays in the gutter. So we can put them in just where they're needed, not everywhere and just because. And we can do that right from the desktop, skipping the effort of having to go out and capture curbs in the field. So we go through the process of editing or modifying the topo surface so that it flows properly and reflects the real world correctly. And the result is a drainage surface or an artificial DEM. What you see here is an artificial stream network in an urban neighborhood built off a modified LiDAR DEM. And the flow goes clearly from right to left, and you can see clearly that there's flow on both sides of the street, in the gutter where you'd expect it. So remember that Cornell was dealing with data at the 900 square meter resolution, and we're dealing with data at the 1 square meter resolution. A couple key points here are that some sinks are actually legit. A low spot on the surface where water accumulates is a sink, and that actually might be where storm drains exist. So we don't want to arbitrarily fill all the sinks. We also want to use the flow accumulation layer as a primary visual for our QC, and that's actually what we were looking at before, was an example of a flow accumulation layer. And we use that as a visual for QC and for fixing the surface where we can see obvious errors. And the result of this whole process is an artificial DEM or a drainage surface. So here's a schematic of the surface editing process. We start by using a really low threshold for filling sinks just to remove any noise that's in the surface. And then we iterate around this loop, turning like a crank each time, generating a new modified DEM. So we'll generate a bunch of derivative GIS layers, evaluate for brake lines, add brake lines, and spit out a new DEM. And we might turn this crank 20 or 30 times as we go through and edit a surface until we think we've got it cleaned up and it's ready to begin modeling. So once we are ready to begin modeling, all this stuff we kind of put in this green box and it goes up here in the upper left. And now we have a surface that we can evaluate against the stream network or against any points that we throw at it in order to generate catchments. So we generate catchments in 2 ways. right? We can throw points and generate catchments from those points, or we can throw a stream network at it and generate catchments for every segment on the stream network. And then as we evaluate the catchments and we look for obvious errors, if we need to, we can go back to the surface and continue editing on the surface before we come back and iterate through this process. So now for some examples of how this actually works. So first up is an example in urban Pittsburgh. This is in the borough of Whitehall, and this is a highly developed residential area in an urban environment. And we can see how flow is coming from the bottom of the screen from the south, and it's coming on both sides of the road. And then something weird is going on, and the flow sort of merges and then splits again. So by judiciously adding in a few break lines, we can correct how the flow performs on the surface model and actually fix it so that the flow on the left side of the road stays on the left and the flow on the right side of the road stays on the right. Here's another example I like where you can see the flow is accumulating from the bottom of the screen, and it's accumulating on the road, crosses the road, heads down into this back parking lot area, and then it heads into the back door of this building, down the main corridor and aisles, and out the front door of the store. So obviously that's not how things work. Remember, we're using digital elevation models where all of the buildings have been removed, right? It's just the bare surface. And so sometimes things like this happen, and we fix that by adding break lines. So if we add a break line here, we can reroute the flow. Instead of going through the building, it'll actually go around the building. So sometimes people ask me, well, how come you didn't just connect the flow in the gutter here and have it route around the building on the front? Because you can clearly see the gutter and the curb along the edge of the road. And the answer to that is in the data. As you zoom in, now we're looking at the LiDAR points, you can zoom in and look at the elevation values of the individual points, and you'll see that it's actually uphill. So the points between here are actually higher. So while we do have the ability in the digital environment to trench in or berm up, and we can route water, it's kind of like a kid at the beach moving sand around. We can do anything we want to, but our intention is to only make changes to the surface model to help it reflect how water flows in the real world. So when we see in evidence that the elevation values are higher here, we let the elevation model do what it does and route the water behind the building into the parking lot. Here are some examples now. I want to shift over to Ulster County in New York. And here's an example project that we worked on in a small catchment area called the Saltkill Creek, which drains into the Esopus Creek, which eventually drains into the Hudson River. On the left is the hydrography network coming out of the mountains, and on the right is the road network. And you can see that the northern part of the road network is up on a mountainside, so there's no roads. But there's a small village center in the middle and a couple of main roads paralleling the primary drainages and crisscrossing the tributaries all over the place. And so what does a self-respecting town highway department do when they want to start a culvert assessment project? Well, they hire a bunch of interns and they send them out with a GPS receiver. And that's what we got. So we got tons of great of culvert inventory data all over the town. And so one of the nice things about this process here that I want to point out is that it's scalable. And you can see in the upper right-hand corner, these boxes in blue indicate the county-managed culverts. And so we can map the drainage area associated with those culverts, which is represented here in pink and in green. But if we're interested in higher resolution, we can actually put in all the town culverts that exist inside those larger drainage areas. So if you want to evaluate the town culverts, that would require some additional cleanup and assessment of the catchment areas to each of these. But if you only want county culverts, you don't have to worry about the details inside the catchments, just the boundaries. So it's a scalable process. You edit the data and clean up the surface model at the scale that you want to analyze. You don't have to look at every single pixel. So as we were working on this project, invariably we get some examples like this, where the surface model is either not performing properly or the fill step is being over aggressive and filling in those shallow roadside ditches. So we can either reduce the fill, which might take care of some of this, but it's going to end up adding more spurious sinks all around the surface model. Or we can leave the fill settings as is and look for situations like this and fix them with break lines. So we can go back through, and by adding break lines, we can actually route the flow and force it to go where we know it needs to go. We also need to look at the GPS data critically, and here's a kind of a classic GPS problem, right? Where's the culvert? We can model any point on the surface model, but the points need to be located properly. So we have to look at where exactly is this culvert in the real world. Is it any one of these 4 points? And that's where having local knowledge or even additional notes in the culvert inventory data set when they're collecting it in the field can help us resolve problems like this with the GPS data. So this is how it looks graphically laid on imagery. So, we throw points on there and we generate our drainage areas, and then we can QC them based on our knowledge of the ground and looking at imagery and LiDAR together. And ultimately, once we have the surface ready, we can start working on this toolbox. So this is we took the Cornell Python scripts and we adapted them into, instead of having just independent scripts that all have to be run independently, we adapted them into a ArcGIS Toolbox construct. So we stack up all the input data sets in this toolbox and hit the go button, and we end up with what we're finally after, which looks something like this, right? Which is a results table for every point in our inventory that we want to throw at it, this facility ID. We generate the catchment characteristics, the area, the slope, the maximum flow length, and the average curve number inside those drainage areas, and the peak flow estimates for the 1, 2, the 5, etc. year storm event. So another nice thing about this is that not only do we have these calculations, but we can take the information on the key characteristics as well as the geography of the polygons, and we can export those out to be used in an independent model. So the process works on any set of points, even catch basins in urban environments, not just culverts. So catch basins, somewhat like culverts, however, have their own issues. So note here how the GPS points, which are these blue dots, they're likely intended to be over the manhole covers, but they're off. And here's a close-up showing where the manhole cover is, which is right this gray spot in here, where the GPS point is, and then where the flow actually occurs, represented by this red line along the gutter. So what we really need to do is move the point from where it is into the flow path, and not leave it located up on the curb or over the manhole cover. Here are some more examples where you can see what the surface model indicates with this flow accumulation surface here represented in blue, and where the catch basin inventory indicates where all the catch basins are. And in some cases, the surface model shows that some catch basins are effectively getting little or no flow at all, where others are getting most or all of it. So this could be a grading issue, could lead to an upsizing retrofit, or the need to add additional drains to the stormwater network. It's also not uncommon at all, excuse me, to see multiple entries for the same structure. In this case, not only do we have multiple GIS points representing one structure, but it looks like there's very little flow that's actually going to that structure regardless. It's actually all on the opposite side of the road. We also sometimes see two physical catch basins side by side, most likely to provide enhanced capacity at this location. So these often exist separately in the inventory as well. So we have two separate points and two separate IDs in the inventory. But we may want to actually model this as one location. So that represents a GIS problem as much as a modeling problem, replacing 2 points in the inventory with 1 in the model, and then moving that point to the correct location in the flow model. But placing the points is not trivial, and it's not something you want to completely turn over to automation. Notice the difference here if you move the points by just 2 cells. These 3 red cells here are actually only 1 cell apart from each other. So if you were to move the point by just as much as 2 cells, you're going to get strikingly different results with the flow accumulation model. So it's important working with local teams to validate the placement of the points and work through some of these issues. Wrapping up, this last example is a hillshade of the LiDAR surface in Whitehall, just outside of Pittsburgh. And I wanted to give you a visual of how once the surface has been scrubbed and cleaned, then we run the full flow model on it. And this is what the artificial stream network looks like from the flow accumulation model. Then we threw over 700 points at this with catch basin locations to generate drainage polygons to each catch basin and then calculate the peak flows. So here's an example of what those results look like. And that allowed the engineering team to go out and prioritize which catch basins to look at, either because they had little or no contributing area, or because they had this massive contributing area. It also allows them to run different scenarios about what happens if any of the upstream catch basins are either undersized or clogged, and that flow just gets pushed downstream to the next catch basin. For example, you may want to design catch basin capacity to not only handle its own catchment area, but that of 1 or 2 catch basins upstream. So the overwhelming conclusion is that it works. It's not something, though, that you can go out, download a DEM, queue up the process, and hit the go button. It's an iterative process, and it does require looking critically at the data, cleaning up the elevation data until you get a surface model that works for drainage. So this presentation and other similar information can be found at the GroundPoint Engineering website. Hopefully you found this helpful. Perhaps even it got you thinking about drainage a little bit differently. If you have any thoughts, questions, or concerns, feel free to give me a shout, and have a great rest of your day. Thanks.